So let's do another truss style example, but this one's going to be a frame. So the truss means all of our forces only have axial loads on them. So let's do another one, and this is let's do this example. Sorry, we'll do frame 01. Okay, so our frame, if you're looking at the slides, is 5 meters tall and 8 meters across, and goes like this. So we have 5 meters and 8 meters. We have a point load applied to it of 250 kilonewtons, and we're going to have unknown reactions that we're drawing placeholders. We don't know what direction they're going to go, but I'm going to guess, and if I get a negative answer, it means they're going in the opposite direction. So our left-hand side for X, our left-hand side for Y, our right-hand side for X, and our right-hand side for Y. So this is our system. Let's label some of these so we can start doing method of sections. Let's call this A, we'll label this B, we'll call this member C, and this member D. We want to solve for all of these internal forces, but the first thing we have to do is we have to solve for what our reactions are. Before we can do anything, we have to solve for our reactions. So step 1, reactions. We know that we have 3 equations we can use. We can sum the forces in the y direction, so upwards being positive. We have Ly plus Ry equals 0. There's nothing else going up and down. So how are we ever going to get reactions in that direction? Well, a force going this way is trying to cause this to spin, and we could have forces going in opposite directions that might be a couple. But we'll worry about that in a little bit. But look at this. Let's rearrange this. Ly has to equal the negative of Ry. There's nowhere else that anything could be, which means that these will be equal and opposite reactions. We don't know what the value is yet, but we know they'll be equal and opposite reactions. Let's sum our forces in the x direction. Let's label our nodes here. Let's call them, what did I call them in my example, just so I'm consistent? Doesn't look like I called them anything. So we'll call that, oh yeah, I did. So 0, 1, 2, and 3. We'll call those the nodes. So let's sum our, find our forces in the x direction. We have Lx in the positive direction, Rx in the positive direction, and we have 250 kilonewtons in the negative direction. So that doesn't give us much. So we still have a bunch of unknowns, nothing really helping us. You could say we have 4 unknowns, except we know that Ly is equal to the negative of Ry. So really we can rewrite this as 1 unknown. So we still have 3 unknowns. Let's solve for the moments rotated about the z-axis, and let's use point 0 to do this. Well, if we're passing through this point, Ly doesn't cause a moment, Lx doesn't cause a moment, and Rx doesn't cause a moment. We have our 250 and our Ry. If we put a pin in the page right here, and we spun the paper in that direction, or curled our right hand in that direction where my fingers are trying to spin it in the same direction, my thumb is pointing out of the page, which is positive. So positive Ry, and it is 8 meters away. And we have our 250 also trying to curl it in the same direction. So plus 250 kilonewtons, and the closest it comes is 5 meters away. And that has to equal 0. Well, it looks like if we rearrange this, we get that Ry equals negative 156.25 kilonewtons. Negative means that we drew our arrow wrong. So Ry really equals 156.25 kilonewtons downward. So from this point on, we can draw the arrow upwards and call it negative 156.25, or we can draw the arrow downward and call it 156.25 positive. It's up to us, both are correct. So now we have our Ry solved. Let's come back up here to our Ly. Ly equals the minus of Ry. Our Ry is drawn upwards, which was minus 156.25, which means Ly equals 156.25 kilonewtons upwards. So we have equal and opposite reactions happening there. We still don't know about Lx and Rx. Maybe it'll help if we start cutting some sections. Maybe we could start trying to find what these values are. Even if we picked another spot to spin this about, we still won't be able to solve it. So let's put that on hold, and we'll come back and see if anything shakes out from when we start doing our method of sections. So let's cut around section 2 or node 2 here and cut through A and D. So we're cutting A and we're cutting D. I don't know what the internal forces are. I'm going to draw them as in tension, so away from the cut. This is point 2, and this node right here is where the 250 kilonewtons was being applied. Let's take a look at that and sum the forces in the y direction. Well, we have D acting downwards and nothing else. So D equals 0. Let's sum the forces in the x direction, with everything in that direction being positive. We have minus A minus our 250 kilonewtons equals 0. We can solve for that, and we get A equals minus 250 kilonewtons, or A equals 250 kilonewtons in compression. Let's take a look at this node here. Let's cut through D and B now. So we're going to cut through D and we're going to cut through B. So B and D. D we've actually solved for, and we already know it equals 0. And we also have at this point our x and our ry we already solved for, ly we already solved for, and we don't know, this is rx and ry, but you know what? I am going to redraw this. We can do it. I could call this ry equals minus 156.25, but I'm just going to redraw it. You can do it either way. Both are correct. D equals 0. B is unknown. Rx and I'm going to draw my arrow downwards with 156.25. If I wanted to keep drawing my arrow upwards, I'd need to include that negative 156.25. So now I need to know what angle B is at relative to the x-axis. Again, you could pick it from the y-axis, but I like to do it from the x-axis so that I have kind of some consistency in how I'm thinking about things. but it might be helpful to find out what this angle is. And I can use similar triangles to find out what the angle is. This was 5 meters tall and 8 meters wide, so I haven't drawn my triangle kind of to the best proportions. But this is the opposite side, and this is the adjacent side. And the inverse of tangent of opposite over adjacent, I can calculate this and I get an angle of 32 degrees. So that's going to tell me that my BY is going to equal B times the sine of 32 degrees, and BX equals B times the cos of 32 degrees. That way I don't need to bother with writing BX and BY all the time, kind of bogging me down in the system. So now let's sum the forces in the y direction, with upwards being positive. And if we sum the forces in the y direction, we have D, which equals 0. We have our BY drawn upwards, which we know BY is B sine 32 degrees. And we have our downwards force of 156.25, or minus 156.25. And this has to equal 0, or we want to know what it takes for this to equal 0. If I solve for this, I find that B equals 295 kilonewtons. It's a positive value, which means however I drew it is correct, and I drew it in tension. So let's just make that note to ourselves. Let's sum the forces in the x direction. So if we sum the forces in the x direction, we have our bx going in the negative direction, and bx is really b cosine 32 degrees, plus our unknown Rx. Well, we can rearrange this. We know what B is. B is 295, so this is really minus 295 cosine of 32 degrees plus Rx equals 0. We can rearrange this and we get that Rx equals 250 kilonewtons. Now, if you remember from before, we knew that Lx plus Rx equaled negative 250. So let's take a look at that. Lx plus Rx minus 250 equals 0. We now know what Rx, so Lx plus 250 minus 250 equals 0, or Lx equals 0. Which honestly really makes sense. There's no way for that reaction to do anything. There's no way for any load to get to that in the x direction. So now we have all of our reactions in the end. So we've solved for all of our reactions. We have solved for our force in A, we've solved for our force in D, and we've solved for our force in B. Looks like we have one kind of member left to solve for. Let's take a section through C. So that's our unknown member C. We have our known reaction here of Ly, which is 156.25 kilonewtons upwards. And we had our Lx reaction that we just determined was 0. So if we sum the forces in the y direction, with upwards being positive, we want to know what it takes for this to be 0. We have C going upwards, plus our Ly, which is 156.25 equal to 0. C equals minus 156.25 kilonewtons, we know that that means, because I've drawn it in tension, the negative number tells me it's actually in compression, that I have 156.25 kilonewtons in compression. So we have our full truss here, or a full frame, with 250 kilonewtons of applied load. Remember, this is all we knew at the beginning. We only knew that there was 250 kilonewtons of applied load on this. We were able to determine that the reactions were 156.25 kilonewtons upwards, 156.25 kilonewtons downwards, and that the full reaction came out over here and was 250 kilonewtons. And then we determined the internal forces of our frame elements. We determined that the top chord was 250 kilonewtons in compression. We determined that the brace was 295 kilonewtons in tension. We determined that this column had 0 kilonewtons in it, and we determined that this member over here had 156.25 kilonewtons in compression. So we've solved for that frame system. So now we know we can start looking at, going forward in the next few weeks, what all of these members would need to be to resist those loads. What can we do to make sure that we have a reduced capacity bigger than all of those loads? So unfortunately, I have to film all of the example videos on my phone, which is a total pain in the behind. So it's a little bit more cumbersome. Okay. You guys would have been following along with the lecture video, which is really heavy on the example side for this week. But now we're going to look at the method of sections for beam 1. So beam 1. And beam 1, they told us that we have a beam that is 15 meters long, and it has a point load applied at the middle of 20 kilonewtons. It's a pinned roller condition, which is really saying that these columns can splay out a little bit. This reaction will end up being 0, and there will be nothing over there because our columns can splay just a little bit. So we have reaction 2, reaction 1, and our X. They've also told us that these are 7.5 meters, so it's the total beam is 15 meters long. So we want to know what the internal forces in this beam are. That's the thing we need to know. And we want to know what the maximum internal forces are, which means we have to figure out what the internal forces are everywhere. So let's start by solving for our reactions. The sum of the forces in the X direction, where that direction is positive, we have Rx equals 0. So that works out nicely. So now let's sum our moments about a point. Whenever I'm solving for reactions, I always pick that node. We're going to sum the moments about the z-axes, and I'm going to use point 1. Everything spinning it in that direction is positive. Anything spinning it in that direction is negative. And I want to know what it takes for this to be 0. My 20 kilonewtons is spinning this in the negative direction, or minus 20 times 7.5 meters. To be a moment, you need a force times an eccentricity. If I put a thumbtack here, R2 is trying to spin this in the positive direction, and it is 15 meters away. Now, I'm pretty sure you could probably have intuitively looked at this and seen that 20 kilonewtons is in the middle, and 10 is going to go to this side, and 10 is going to go to this side. Well, let's just check this out. If we solve for this, we get that R2 does in fact equal 10 kilonewtons. Now we can sum for the forces in the y direction being set to 0, upwards being positive, and we have R1 upwards, we have our minus 20 downwards, and we have our R2 upwards, which was 10 kilonewtons. And all of that has to be equal to 0. When we rearrange this and solve for R1, it also turns out to be 10 kilonewtons. So that makes sense with what we had intuitively started with. Let's now start talking about our internal forces in this. We're going to do the same thing we did when we solved for a truss. But remember, the top chord and bottom chord make a couple, and our web is acting like a shear strut. So we can make a cut of a single member in bending and replace those unknowns as a placeholder for the internal forces of shear and moment. So let's take a look at that. I'm going to pick a spot to cut. I don't know where I'm going to cut. I'm going to make a cut. I'm going to make a cut at 3.75 meters. So let's make this cut right here. I'm going to say that this is at 3.75 meters. I have 10 kilonewtons here. Remember, this 10 kilonewtons is fully dependent on the 20 kilonewtons that's been applied. And I'm making this cut here. So I'm going to use a placeholder for my shear and my moment. People often ask me why I only draw half of the arrowhead when I draw this. It's kind of just convention, because what I'm saying is I'm trying to look at these two spots slipping past each other, and I'm actually only drawing one half of my arrowhead. It's just a way we tend to kind of do a shorthand to indicate that we're talking about shear in these drawings. You can draw a full arrow, it's not a problem. I've just been drawing these for so many years that, and I just tend to follow the industry standard where I cut my arrowhead in half for shear. So these are placeholders. I don't know what these values are. So we want to use our method of sections to solve for these. And remember, I've made this cut right here. So let's sum the forces in the y direction, where upwards is positive. We have 10 kilonewtons upwards, and we have our unknown shear acting downward. I could have drawn this shear whatever way I wanted. Again, habit is I draw it downward when I make this cut, just because I kind of know what answer I want to end up with. You could draw it upwards. It's not going to matter. Positive and negative has very little meaning for shear. What's really important is just keeping track of which side it's on. So keeping track of the positive and negative is important, but it has no real meaning contextually. For axial loads, it made a big difference whether something was in tension or compression. It's not going to mean much for us with shear loads. So we have our 10 kilonewtons upwards, our unknown shear downwards. We can rearrange this and we get shear equals 10 kilonewtons. So the shear at 3.75 kilonewtons is 10 kilonewtons, 3.75 meters. Our internal shear is 10 kilonewtons. We now have an internal force in our beam that we can start to use. We can start to look for the things or the elements that are strong enough to resist those loads. Let's sum the moments about the z-axis, and I'm going to make my spin about my 3.75 meter cut. This is mostly so I don't have to deal with my shear force. If I had wanted to jump right into my moment, I didn't need to worry about my shear. I happen to have solved it, so I could have picked over here. It's not going to matter, but I like to start by making my moment spin about the point I've cut. Again, you can pick whatever point you want to do it about, but this is going to be pretty handy for us later on. And so some of that is experience. So I'm going to suggest when you're cutting a beam, wherever you're cutting it is a good place to start spinning your moments about. So we have about this point here, the shear passes through it, so it doesn't cause a moment. Our 10 kilonewtons tries to spin it in this direction, which is negative, our negative direction, so minus 10 times, and we're 3.75 meters away. And the other thing causing a moment is our unknown moment, which is trying to spin it in the positive direction. Again, I've picked drawing it in the positive direction. So plus moment equals 0. If I rearrange this, I get that the moment equals 37.5 kilonewton meters. So at this point right here on our beam, we have an internal shear of 10 kilonewtons and an internal moment of 37.5 kilonewtons. Well, that doesn't help us completely. It's certainly starting to paint a picture for us, but we need to know what the maximum shear and the maximum moment is, and we don't know if these are the maximums or not. So we're probably going to need to make some more cuts. Now I can tell you that the best place to make cuts is where we see a change. So if something's just continuing along, maybe we don't really need to make a cut there. I am going to pick a few points that I think would be really important to make a cut. I'm going to make a cut just a hair on this side of the reaction. So when I say just a hair past, I'm talking about 0.0000000000001 past the reaction point. I'm going to make the cut here, which is the one we just made. I am going to make a cut 0.00000000001 to this side of the force, so small that we could probably just call it 0. But then I'm going to do the same thing on the other side, or 0.00000000001 on that side of the applied load. I'm going to do the same thing here, and I'm going to do the same thing here. So we've already made this cut right here. Let's do the one on this side of the reaction. So let's make our cut right here. We have our R1 here, which is 10 kilonewtons, and we have an unknown shear and an unknown moment. If we sum the forces in, just want to see where I've done this. If you wanted, you could even say, you could redraw this if you want and just say that that distance is 0. So we are going to sum the forces in the y direction just shy of that location, or just after R1. And we are going to see that we have our 10 kilonewtons going upwards and our unknown shear going downwards. So remember now this is a different spot, so a different shear. We're going to rearrange this equation and we're going to get that V equals 10 kilonewtons. We're going to sum the moment about the Z direction, and we're going to do it at our cut, which is pretty much essentially right at 0. So we have our 10 kilonewtons going upwards, our 10 kilonewtons passing right through the load, so 0, because the eccentricity is 0. V is going downwards, so minus 10, but it's also times 0. And we have M trying to spin it in that direction, which is positive, so plus M. When we rearrange that, we have 0 moment at that location. So let's maybe, we'll sum these up a bit later. We had, let's just write this for self. This was at 3.75 meters, and this was at 0, or 0.00000000001, if you wanted to look at it that way. Let's do it at 7.5 meters. Left side of load. So let's do it just a hair before the load is applied. So let's draw this out. We're cutting this at 7.5 meters. I just need to see what time it is here because I'm gonna have to get my kids from the babysitter who's watching them while I film this. We have our 10 kilonewtons, and we have our unknown internal shear and our unknown moment. We can sum the forces in the y direction, with upwards being positive. We have 10 kilonewtons minus our unknown shear equals 0. V equals 10 kilonewtons. We can sum the moments about our cut here, so about the z-axis at our 7.5 meter mark. And we have 10 kilonewtons trying to spin our beam in that direction, or 10 times 7.5. V is passing through it, and our moment is trying to spin it in that direction, or plus moment equals 0. We rearrange this, and we get that our moment equals 75 kilonewton meters. Sorry, that should have been a negative because it's trying to spin it in that direction. So minus 10 times 7.5. So now we've done our third cut. Let's do our fourth cut at 7.5 meters, right side of load. So let's do the same section cut, but now we're just a hair on the other side of the load. So 7.5 meters, we've got our reaction of 10 kilonewtons. We've got our applied load of 20 kilonewtons, and we've got our unknown shear and our unknown moment. We can sum the forces in the y direction with upwards being positive, and we have 10 kilonewtons upwards, 20 kilonewtons downwards, and our shear downwards. We rearrange this and we get shear equals minus 10 kilonewtons. Positive and negative doesn't really mean much for us for shear, but let's keep track of that. We'll keep track of the fact that that's a negative. Now let's sum the moments about the z-axis, where everything spinning in that direction is a positive. And again, we're going to make we're going to spin it about our 7.5 meter mark. We have 10 kilonewtons trying to spin this in the negative direction, 7.5 meters away. 20 kilonewtons passes through the point, V passes through the point, and we're left with our positive moment. So M equals 75 kilonewton meters. So we've made our fourth section in method of sections. Let's pick the one that is now at 11.25. 11.25, right? Yeah, 11.25 meters. So now we're doing another cut where we're 11.25 meters. We've got our 20 kilonewtons of applied load. This is 7.5 meters. We have our reaction here of 10 kilonewtons and our unknown shear and our unknown moment. So let's sum the forces in the y direction with upwards being positive. We have our 10 kilonewtons upwards, our 20 kilonewtons downwards, and our unknown shear downwards. We rearrange this and we get shear equals minus 10 kilonewtons. Let's sum the moments about the z-axis and let's pick our 11.25 point. We have our 10 kilonewtons, so we're going to spin it about this point right here. We have 10 kilonewtons trying to spin it in that direction, which is our negative direction, minus 10 times 11.25. We have our 20 kilonewtons trying to spin it in the positive direction, so plus 20 times, and we've got 11.25 minus 7.5. We could build that right into our equation, or we can do that math. We've got 11.25 minus 7.5. Oh, look, we've got 3.75 there. So times 3.75. And then our shear is passing directly through it, and we have our unknown moment in the positive direction. We can rearrange this, and we find that our moment equals 37.5 kilonewton meters. All right, let's do our last one, which is the one just before our reaction 2. So we have 15 meters. We know our load is applied at 7.5 meters. How am I for time? Oh, I'm so tight. From current slide, we have our 20 kilonewtons of applied load. We have our 10 kilonewton reaction, and we're just shy of our reaction on this side. We have our placeholder for shear and our placeholder for moment, where we don't know what the internal forces are. This is what we want to find. We want to know what these need to be for this system to be in equilibrium. 15 minus 7.5 means that this is 7.5 over here on this side. Sum our forces in the y direction, where upwards is positive. We've got 10 kilonewtons minus 20 kilonewtons minus v equals 0. We've got v equals minus 10 kilonewtons. If we sum the moments about the z-axis, where everything in that direction is positive, so we're summing everything about that node right there, which is our 15 meter mark. We have our 10 kilonewtons trying to spin it in that direction, which is minus 10 times our 15 meters. We've got our 20 kilonewtons trying to spin it in the positive direction, so 20 kilonewtons times 7.5 plus our moment equals 0, m equals 0. So we've solved this at all the points that we could. Let's take a look at what that means. So x, v, and m. At 0, our shear was 10 kilonewtons. At x equals 0, our moment was 0. We checked this at 3.25 meters, 7.5 meters, a second 7.5 meters, 11.25, and 15. We solved this and we got 10 and 10, and then we jumped. We switched to minus 10 and minus 10 and minus 10. For our moments, we got 37.5, and then we got 75 and 75, both times we did it, and then we got 37.5 and 0. Now this is where it's often helpful to draw these out. Let's take a look at what this means for us. 1, 2, 3, 4, 1, 2, 3, 4. We had 10 and 10 and 10, and then we jumped to minus 10, like that. So this is V, or our shear force diagram. In kilonewtons. And this is 10, and this is minus 10. And these are really handy because they start to show us what's happening. We had 0 and 0, 37.5, 75. Sorry, 75. So this is our moment, or our moment diagram. In kilonewton meters. And this really kind of helps illustrate that our maximum shear was 10. Whether it was positive or negative, it didn't really matter. The value was both the same. And for our maximum moment, it was 75 kilonewton meters. And this happened at L equals 0 and 15 meters. And this happened at L equals 7.5 meters, or the halfway point. And we might be able to figure something out about that in a little bit, but I'll record that in a separate video.